The fourth and arguably final step in our pentose or our non-oxidative phase of the pentose phosphate pathway is one that appears a little bit complicated, but it isn't quite so complicated, especially whenever you step back and take an overview of the entire pathway. So the reaction that I'm talking about is this one depicted down here, number 8. And that number 8 reaction is a transketalase reaction. What I want you to recognize about the pathway is actually, if I go back, what we've done before is we've used one of these ribose 5-phosphate and one of these xylulose 5-phosphate. So we accounted for 10 of our 15 carbons at that point in time, leaving behind one xylulose 5-phosphate molecule. Now that xylulose 5-phosphate is a ketose, erythrose 4-phosphate is an aldose. What we're going to do is we're going to do a transketalase reaction. And so what we are going to be working with is these first two carbons, we're going to move those onto carbon number 1 of erythrose 4-phosphate. And in the process, we're going to generate fructose 6-phosphate. Now, one of the reasons that I think that this is a little bit confusing, and one of the reasons that I strongly recommend counting the carbons and keeping track of the total number of carbons, is because I think it makes it a little bit more clear about where different atoms are coming from. Because one misstep, I'm going to erase this, is if you were to add up, so split this, left-hand side, right-hand side. If you were looking at this slide and looked at it on the left-hand side and you said, well, fructose 6-phosphate, that's 6 carbons. Erythrose 4-phosphate, that's 4 carbons. Xylulose 5-phosphate, that's 5 carbons. 6 plus 4 plus 5, well, that is going to be 15, okay? Then move on to the right-hand side. We said fructose 6-phosphate, 6 carbons. Glyceraldehyde 3-phosphate, 3 carbons, 9. Well, where did the other 6 carbons go? That's one of the things that I think is inherently not necessarily problematic, but can be problematic. So what I always like to do is I like to account for the carbons because I think that it's helpful to think about what is being added to what. In addition to that, in this figure, I like that they've color-coded it. If you look here, we've got this kind of light green box around carbons number 1 and number 2. We also have carbons that are green versus carbons that are kind of a burgundy or a maroon. Well, in this fructose 6-phosphate molecule that we generate from our transketalase reaction, well, we're going to generate a molecule with carbons number 1 and 2 that are green from our xylulose 5-phosphate, and carbons 3 through 6 that are a maroon or burgundy from our erythrose 4-phosphate. The other product that's going to be generated is this 3-carbon long molecule from xylulose 5-phosphate. That molecules are glyceraldehyde 3-phosphate. So it's 3 carbons. They are green carbons, or they are just depicted in green right here, right here. Now, what does that mean for this fructose 6-phosphate? Well, what that means is that fructose 6-phosphate was already prepared. It was made in our previous step. So arguably, you could kind of look at the end of the pathway in some respects as generating 2 fructose 6-phosphates and a glyceraldehyde 3-phosphate molecule. But with that in mind, if we look at the pathway as a whole, one thing that's very important to recognize is that these steps right here, those are all reversible steps. Just as going back to ribulose 5-phosphate is a reversible step. But I always like to, or I think it's important to recognize that these are, yeah, it's nice to think about it going in like a constant cycle, and it's a constant spin. But I think that it's important to think about each one of these molecules, and it's one term that you may hear from time to time is a carbon sink. I always like to think about these as reservoirs. So whenever there's an excess of glucose, you can make some glucose 6-phosphate. And that glucose 6-phosphate can go through and it can fill up the glyceraldehyde 3-phosphate, the glyceraldehyde 3-phosphate, the acetoheptulose 7-phosphate, and the fructose 6-phosphate. You can fill up, not necessarily all the way, but you can add enough of each one of these components so that this pathway can be initiated when one of these molecules is needed. So when ribulose 5-phosphate concentrations are very low, but concentrations of glyceraldehyde 3-phosphate and acetoheptulose 7-phosphate are higher, well, what can you do? You can do this transketalase reaction in reverse. Generate that ribulose 5-phosphate and the xylulose 5-phosphate. So it's important to think about these, and I think that it's very helpful to think about these pathways, or this pathway in particular, as basically filling these kind of reservoirs with these different molecules. Now, with that in mind, I'd like you to think about our oxidative phase and our non-oxidative phase. I'd like you to think about them as simply as possible. So our non-oxidative phase is a redox, a hydrolysis, and a redox reaction. That's all there is to it. In the process, you're generating 6 NADPH, and it doesn't not matter, but you're also generating 3 CO2. Okay. Now, our non-oxidative phase, if you look at this, if you look at the non-oxidative phase here, well, we're not generating any NADPH, so I'm going to put 0 NADPH. And then if you look at any other byproducts, for instance, CO2, you're not generating any CO2. You know, I talked about this non-oxidative phase having more or less like a crosstalk with other metabolic pathways. But this non-oxidative phase kind of goes in a circle. It's kind of a pathway that just kind of continuously goes. Nowhere in there is molecule X being generated as like a target. You're making glyceraldehyde 3-phosphate. This and this could go off to DNA synthesis. You're also making ribose 5-phosphate. Or sorry, glyceraldehyde 3-phosphate. That would be going through glycolysis. Or ribose 5-phosphate could go on to DNA and RNA. So you have these different reservoirs that are being filled up. Now, with that in mind, and I want to simplify kind of our reactions of this non-oxidative phase. I'm going to go ahead and draw my defining line between my oxidative and non-oxidative phases. In my non-oxidative phase, the first reactions that I have are simply rearranging of 3 of my molecules. And so I have an isomerase or an epimerase. Now, the difference between them is with our isomerase, we're taking a ketose to an aldose. Ribulose 5-phosphate is a ketose, and ribose 5-phosphate is an aldose. Our epimerase, well, our epimerase is just rotating the OH on C3. Ribulose is a ketose, xylulose is a ketose. And you're simply making a C3 epimer of ribulose 5-phosphate. So that's kind of your first portion of the non-oxidative phase. After that, it's a transketalase reaction, followed by a transaldolase, followed by a transketalase. I think that's the most helpful way to think about this pathway. It's a transketalase followed by a transaldolase followed by a transketalase. Sure, each of the components, each of the steps of the non-oxidative phase are reversible steps. But that's not to say, or so it's important to think that although this reaction can go forward and it can go in reverse, you kind of have to pick a direction in which you want to go. And so for me, it's most helpful to think about kind of going in a counterclockwise fashion. I start with my ribose 5-phosphate and xylulose 5-phosphate. I make my glyceraldehyde 3-phosphate instead of heptulose 7-phosphate. I make the fructose 6-phosphate erythrose 4-phosphate. Then from there, I use xylulose 5-phosphate and erythrose 4-phosphate to make fructose 6-phosphate and glyceraldehyde 3-phosphate. Sure, I could go in the opposite direction. And I could distract myself with saying, okay, well, which direction is it possibly going in? But if you keep this in context, if you keep this in mind of going in one direction and then going in the reverse direction, I think that's a helpful way to think about it, because this is a pathway that is not like glycolysis, where it's simply linear, and you start here, you end here, you get these products along the way. Well, this all is the pentose phosphate pathway in a nutshell. We talked about the different types of reactions. We accounted for lots of the carbons that are present in our molecules. We talked about similarities between these reactions, or similarities between the molecules, and how they're basically all kind of serving as reservoirs for different pathways. The primary purpose for the synthesis, or sorry, the primary purpose for the pentose phosphate pathway, however, is the generation of NADPH. We generate that NADPH in our oxidative phase. Then we generate our second most important metabolite, ribose 5-phosphate, in our non-oxidative phase. And we do that in our first reaction of our non-oxidative phase. At any rate, I hope this was helpful. I hope this is an adequate overview of the pentose phosphate pathway, a pathway that's kind of doesn't get the same pomp and circumstance that glycolysis or gluconeogenesis get, but nevertheless an important pathway, and one that is kind of a pathway that feeds into glycolysis. I mean, heck, we're starting with the first step in glycolysis, that glucose 6-phosphate. We're generating NADPH, but we're also getting glyceraldehyde 3-phosphate, which is one of our major metabolites in glycolysis. All right, well, I hope this is helpful. I hope you have a good one.